Hi Year 12. Let's take a look at some of your topic 1 multiple choices that I have printed off for you. So it starts off pretty easily. It asks you which lists 1 scalar and 2 vector quantities. So it's just a case of going through and looking and deciding whether they're scalar or vector. So mass is scalar, momentum is mass times velocity, velocity is a vector, so this is a vector. Potential difference is voltage, that's just a scalar, so it's not A. Again, power is scalar, so that's 2 scalars there, so it's not B. We've got power and intensity, again, are just scalars, vector, so it's not C. So this is just a memory game. So sometimes IB questions are easy, sometimes they're not, though, as you will see with some of the next ones. So in question 2, a little bit so we can see the whole question. We've got 2 sets of data shown below with circles and squares. The size of the error bars are the same for all points. So we know then that the size of the error bars tell us the absolute uncertainty in our values. So we know then that the absolute uncertainty is going to be the same for both. Okay, so therefore we know that it's C or D, and we can get rid of A and B. Okay, now fractional uncertainty, remember, is delta x over x. So it's the absolute uncertainty in a value divided by the value itself. Now, let's look here. This y-intercept is 1. This y-intercept is 3. Okay, and clearly it's plus or minus a half. Okay, we don't even really need to do the maths if we just visualise, but I'll do the maths to help you out a little bit. So for the squares, our absolute uncertainty is 0.5, and that's over 1. For our circles, that same absolute uncertainty is now over 3. Okay, now hopefully you can see that this is a much bigger number and therefore we pick larger for squares. So it is a case of just looking. So next up, question 3. A student is measuring the length and width of a rectangular tabletop. What is the absolute uncertainty of the perimeter? So to get the perimeter, obviously we're starting from 1 point going all the way around. So we're doing a length plus a width plus a length plus a width. If we add data together, we add the absolute uncertainties. Okay, so therefore we're going to add 0.1 plus 0.2 plus another 0.1 here plus another 0.2 here. Now hopefully you should see that that adds up to 0.6, giving us B. Question 4 is a fundamental units question. So what is the unit of power expressed in fundamental SI units? So power, P, is work done over time taken. Now work done is not fundamental, so let's break that down. Work done is force times distance. Force is not fundamental, so let's break that down. Force is mass multiplied by acceleration. Then multiply that by distance divided by time to get power. Okay, so we know that for mass, the fundamental unit is kilograms, so that's that one sorted. Acceleration is meters per second squared, that's that one. Distance is in meters per unit time is seconds minus 1. Now let's combine like terms. We've got 1 kilogram, we've got 2 meters, and we've got S minus 3, which gives us answer D. Now, unfortunately, with IB questions sometimes, it requires you to have covered the whole course to be able to test a certain topic. So, case in point, which is a correct unit for gravitational potential? Now, obviously, you haven't done topic 10 yet, so you don't know what gravitational potential is. Just to illustrate the point, though, I have gone through it. You've got an equation in your data booklet anyway, so you actually could do it even without really understanding what the equation means. G is the gravitational constant, the unit of that is in your data booklet. M is a mass, R is a distance in this case, and it is just a case of number crunching, so it's all of this multiplied by a kilogram divided by a metre. I lay it out, I gather like terms, and I end up with my final answer. Now obviously I don't expect you to be able to do this in the test next week. I'm not going to give you questions that rely on things that you haven't been taught yet, but I still think it's important for you to see the kind of topic 1 questions that come up that link to other topics, hence why I've kept it in here now. Okay, question 6. Which quantity has the same units as those for energy stored per unit volume? So I think the first thing we need to do is work out the units for the energy stored per unit volume. Okay, energy stored is work done. We know that's force times distance, we just talked about that. That's mass times acceleration times distance. Per unit volume, volume is volume is measured in meters cubed. So we've got mass, acceleration, distance divided by meters cubed. I gather like terms again. I've got 1, 2 minus 3 m's, so that gets me my m minus 1. Okay, so now I have my base units for energy stored per unit volume. And then I just need to check through and see which one matches. Now this is where it does require you to remember some things from IGCSE. You don't want to be flicking through data booklets for things like this. It's a complete waste of time on the paper, and you don't get equations like this. So density is mass over volume, clearly doesn't match. Force is mass times acceleration, doesn't match. Momentum is mass times velocity, does not match. Pressure, which is force over area, which is the same as mass times acceleration over area, does. You can pause and check that. A slightly easier one for question 7, a list of 4 physical quantities. I've just written it down before I've even got to the answer. Acceleration is vector, energy is scalar, mass is scalar, and temperature is also scalar. Clearly there are 3 scalars. Don't get confident and over cocky with this. I would take the time to write it. You would be surprised how easy it is to just slip and make a mistake. So I would take care. Okay, question 8, another fundamental units question. Which quantity has the fundamental units of kg, m-1, s-2? So I took each variable in turn, took the equations. So energy is work done, is force times distance, is mass times energy, mass times acceleration times distance. Sorry, it's very late over here. So you can see I've broken that down. Same for force. You can just pause and take a look at this rather than me just talk at you with letters. Momentum, I've done the same, and again you'll see we get to the point where we prove that pressure has those fundamental units. Take the time to write on your paper, okay? You need to do that. Do not rely on doing things in your head. I promise you now, it will not work at IB. Okay, 9 is where it's a little trickier. So it says an object is held in equilibrium by 3 forces of magnitude F, G and H that act at a point in the same plane. Okay, so we've got F being up to the left, G horizontally to the right, H down. Now equilibrium means that there is no resultant force on an object. Okay, it's just being held stationary. And we know that it creates a closed vector triangle. Now, what I have done is I have taken vector F and I have split it into its component parts, F sine theta and F cos theta. Now, the reason that I've done that is so that all of my forces are now either horizontal or vertical. Okay. Now, these questions catch people out a lot because you might spot something is right and then choose the wrong one. So, let's have a little look. We know that if we're in equilibrium, this object is not moving. So, resultant force is 0, which means that forces to the left have to add up to equal forces to the right, and up has to equal down. Okay, so in our horizontal plane we have G to the right and F cos theta to the left. They have to be equal to each other, else the object is going to move left or right. Okay, now we're going to kind of reverse our resolving and almost unresolved. So we've got G. If I want G's component along the line of F, I have to move through angle theta. Okay, so I can actually resolve and say that G cos theta must act down the slope that is opposite to F. Okay, these two angles are the same. I also know that H is sweeping through here, must be H sine theta, because I have a right angle here. Okay, so think about what we did with our resolving vectors. Now, again, remember that along one line the forces have to add up to 0. So now if I'm the object here and I've got the force pulling up this way, and I have G cos theta and H sin theta pulling down this way, the sum of these two have to add up to the force pulling up in this direction. And so actually F does equal G cos theta plus H sin theta. Okay. Lastly, let's look at F as G plus H. This is not going to be the case. Okay, if we know we've got a closed vector triangle, we've got G this way, we've got H this way, and we end up with F in this direction. But again, in terms of magnitude, we could argue that G squared plus H squared must equal F squared, and so we don't have F equals G plus H, so this is not true. So therefore 1 and 2 are true. I choose A. We're going to do a lot more with resolving things like this, so if you found that tricky, don't panic. When we get to our next topic, mechanics, we'll practice that lots. Okay, question 10, halfway through. Again, this is one that if I gave it to you next week, you would be baffled because you haven't heard of specific energy and energy density yet. That's topic 8, energy production. But given that I can tell you what the equations are, you should be able to work it out. So specific energy is the energy stored per unit mass. Energy is in joules, mass is in kilograms. Again, energy per unit volume. Okay, that would be a straightforward question at the end of the IB course because you would remember those equations. Okay, a student wants to determine the angular speed. Again, don't panic. This is something that you don't know about yet. This is, let me think, that's topic 6. It's circular motion. Don't panic, that doesn't matter because they give you the equation. It's actually irrelevant. The period t is 0.5 plus or minus 5%. The angular speed is given by 2 pi over t. Well, 2 and pi are just numbers. They're scale factors. There's no uncertainty with a value, okay, with a constant with 2 or pi. So therefore, I can say omega is proportional to 1 over t. I'm dividing by data, so I'm interested in looking at the percentage uncertainty in t. I'm told the percentage uncertainty is 5%, so therefore I must also have a 5% uncertainty in omega. Okay, 12. So again, this one technically is topic 3, so thermal physics, but it doesn't matter, you can do it. A student models the relationship between the pressure, P, of a gas, and it is expected that you remember from GCSE that pressure is force over area. Okay, you have to come to IB with a vague idea of some equations, or you're going to find it really hard. So if you think you've forgotten all of your IGCSE equations, go back to my sheet and make sure you've had a look at them. So you also know temperature is T. they tell you the units are Pascal and Kelvin for P and T. Okay, now firstly, to get a value of P, which is a Pascal, a pressure value, I have to be adding two pieces of data. Both of these must be also measured in pascals to add up to a Pascal value. It wouldn't make sense for, I don't know, let's give an example, a chocolate bar to be equal to a chocolate bar plus some Skittles. That doesn't make sense. Everything that we're adding together has to have the same units. So I know then that both of these are going to be Pascal values. So it's easy to choose X first, so we can sort this out. I know that a Pascal is force over area. Force is mass times acceleration. That's divided by area. Mass, kilograms. Acceleration, meters per second squared, divided by meters squared for area. So I know then that a Pascal is this in base units, so therefore X must also have those. So we can get rid of C and D, process of elimination. Now, Y multiplied by T gives me a Pascal value. I know that T is measured in Kelvin, capital K, a temperature value. Okay, and so therefore Y must be a Pascal divided by a Kelvin, such that when I multiply these two together, the Kelvins cancel out. So I'm saying Y must be a Pascal per Kelvin, so that when I multiply these two things, I end up with a Pascal value. So all I'm going to do is whack a Kelvin to the -1 at the end of it. And that's what gives me answer A. Okay, number 13. So a student measures the radius of a circular plate to determine its area. What is the fractional uncertainty? So again, this requires you to remember the equation for the area of a circle, which is pi r squared. Now, pi is a constant. There is no uncertainty associated with it. So the only uncertainty comes from r. If we raise r to a power, we need to multiply the fractional uncertainty by that power. So we've got two lots of the fractional uncertainty in r will give me the fractional uncertainty in A. Okay, so therefore I must have two lots of delta r over r. That's the absolute uncertainty in r. That's the value of r. The ratio of the two is the fractional uncertainty, so I know I just choose A. 14. What is the unit of electrical potential difference expressed in fundamental SI units? So from GCSE, voltage potential difference is work done per unit charge. We've said a number of times now in this video that work done is force times distance, which is MAD. Charge is current multiplied by time. I need to do that to get my fundamental units. So for M, for mass, I've got kilograms. For acceleration, I've got meters per second squared. Distance is in meters. Current is amps, but it's 1 over current because it's on the denominator, so it's a to the -1, and it's 1 over time, so it's s minus 1. I gather my like terms. I've got 1, 2 meters. I make that a 2. I've got s minus 2, s minus 1. I get s minus 3. I choose my correct answer. 15. Now the database that I have for IB questions, its search engine is terrible, and when I search topic 1, sometimes it throws some other random questions in. But anyway, this is about gravitational potential energy. We actually do know that that's equal to mgh. It asks if we have a weight of 6.1 times 10 to the 2 newtons, and it moves through a height of 8 meters. What is the change in energy? Now this is actually worth us going through, because remember, on this paper you do not have a calculator. Can't spell, sorry, it's very late over here and I am tired. Okay, you can't just type these numbers into a calculator because you don't have one. So this is where approximation comes in and a bit of estimation. To make my life easy, I'm going to call this 6. It's close enough to 6 times 10 to the 2. 6 times 8 is 48. I can do that in my head. I'm not going to find it quite as easy to do 6.1 times 8 in my head quickly. If your mental maths is excellent, cracking. But I find approximation makes my life easier. I know though that this is an underestimation, okay, because actually in reality it was 6.1. The next thing you should notice is these are all very similar, but the difference is the number of significant figures. So the question is a significant figures question. Okay, I go with the lowest. I have to give to 2 significant figures. Okay, and that gets me B. Okay. 16, we're verifying an equation and we want to know how to find the percentage uncertainty in x. 2 is a constant. It doesn't have an uncertainty, so we're not interested. We know that we're multiplying lambda by y and then we're dividing by x. We know that when we are multiplying or dividing, we have to add the percentage uncertainties. Okay, that's just the rule you have to remember. So all we do is we add the 3 together. So we've got 10 plus 0.05 plus 5. Gives me 15.05, but to do significant figures, that is 15. Okay, so just choose your closest one there. Now, 17 is absolutely horrific because you have not yet done the higher level quantum physics topic. This is going to look hideous, but I would like to go through it with you actually because it shows you how to manipulate the numbers on a non-calculator paper, and that could be helpful in future. A proton has momentum 10 to the minus 20 Newton seconds. Okay, fine, it has some momentum. And the uncertainty in the position of the proton is 10 to the minus 10 meters, so we're not sure where the proton is by plus or minus this much. What is the minimal fractional uncertainty in the momentum of this proton? Now, you have never seen this equation. This is called Heisenberg's uncertainty principle. Don't worry at all for a minute what that means, okay? I'm just going to tell you what each of these letters means, and it doesn't matter that you don't have an understanding of what this actually means in context. Delta X is my uncertainty in X. Delta P is my uncertainty in P. So this is my uncertainty in position. This is my uncertainty in momentum. Now, when we get to this topic, you will learn that that has to be greater than or equal to h over 4 pi. Now, 4 and pi are things that you're happy with, but h is something you've never heard of before. This is called the Planck constant. Again, don't worry about that for now. Okay? Ignoring the fact that you are completely baffled by the equation, I can rearrange and pull delta x down. And I'm left with my uncertainty in momentum, which I know I'm going to need because I'm asked for it. Now, h is a constant, the Planck constant, that's in your data booklet, so I've just popped the number down. 4 pi is here. Delta x is my uncertainty in position. I am told that in the question, so I know that I can put my 10 to the minus 10 here. Now this is why I want to show you the question, because I know that pi is roughly 3-ish, give or take. So I'm now just going to call this 12, because 4 pi is around 12. I'm going to call this 6 as well, just to make my maths as easy as possible. Okay, I'm trying to get to a ballpark figure. 6 over 12 is 0.5, and that allows me to simplify this whole thing down. If I'm doing 1 over 10 to the minus 10, I'm doing the same as multiplying by 10 to the 10. So I've got minus 34 plus 10. So that means I'm left with 0.5 times 10 to the minus 24. I can then write that in proper standard form as 5 times 10 to the minus 25. Therefore, this is helpful for you to have seen because it's just me showing you how to deal with the fact that you don't have a calculator in this paper and you don't know how to do 6.63 divided by 4 pi in your head, we simplify. Okay, so I now have an expression for the uncertainty in the momentum. Remember that fractional uncertainty is just absolute uncertainty divided by the value. So now I've got my absolute uncertainty and I was told the value. Okay, so I can do this now, and I can see that this is the same as 10 to the minus 25 plus 20, because I'm doing 1 over to the minus 20. And that leads me with my 10 to the minus 5. Sorry, I've missed a minus sign there. Okay, please don't panic. I'm not going to give you something this difficult next week because it requires you to have done a whole load more. But I hope that you could vaguely follow what I was doing there so that you have seen it. And then when we get to topic 12, you will be able to do questions like that. Getting back to a more simple question, what is the unit of power expressed in SI units? We have seen this. Okay, I've shown you this a couple of times in this document alone. Notice that this is really common. IB repeat themselves. Okay, practice makes perfect because you'll see the question come up again and again. Work done over time taken is power. Work done is force times distance. That's mass times acceleration times distance. We divide that by time. Okay, I then just plug in kilograms for mass, meters per second squared for acceleration, distance is meters, per unit time, that's seconds to the minus 1. Okay, I simplify that down and I get to D. Okay. Again, this is one that shouldn't really have been put in the topic 1 database, but it was. I'm going to go through it anyway, because if you use your IGCSE knowledge, you can actually break this down. You can see how amplitude of a wave varies with position or with time. It asks for the speed of the wave. The wave speed equation, which again we will do in topic 4 and topic 9, is V equals F lambda. F is frequency, which is the reciprocal of the time period. I can get my time period. Notice that at IB, they catch you out. That's in milliseconds. You need to make sure you include 10 to the minus 3. That simplifies to 100 hertz. We'll practice that lots when we do topic 4 and topic 9. Lambda is just the wavelength from one point to the next identical point. That's 8 meters. So I'm just doing 100 times 8, and that gets me 800 meters per second. But again, this is not really a topic 1 question. Last but not least is 20. The length of a side of a cube, so if it helps you sketch it out, is L. We know that the volume is length cubed, hopefully, for a cube. The mass of the cube is given with its percentage uncertainty. What is the percentage uncertainty of the density? Well, we write the density equation first. Density is mass divided by volume. I can express that in terms of length because that's what I've been given. Mass over length cubed. I find the percentage uncertainty in M, the percentage uncertainty in L times 3 because I've got it raised to the power of 3. And I add them together, and when I do that I get my final percentage, giving me 20. So there you go.